Alrighty, we're getting to the cool part, guys. We're getting to the juicy sections of the chapter. Section 2.4, the free particle. Let's get right into it. You're going to see this chapter is a bit crazier than the past few. We turn next to what should have been the simplest case of all, the free particle, v of x equals 0 everywhere. Classically, this would just be the motion at constant velocity, but in quantum mechanics, the problem is surprisingly subtle. The time-independent Schrodinger equation reads, same equation, we just don't have the v. Or, if we reposition stuff, we get this here, which looks like a scenario we've gotten many, many times, where k is equal to square root 2m e over h bar. So far, it's the same as inside the infinite square well, equation 2.24, where the potential is also 0. This time, however, I prefer to write the integral solution in exponential form instead of sines and cosines, for reasons that will appear in due course. So we are writing the solution like this. Although the solution to this in the square well, we said it was a sine or a cosine, so to get the general case, we add them. But using Euler's identity, this thing can expand into a summation of sines and cosines. There's just an I in front of the sign, which makes things a bit confusing to me, but we're going to keep going. Unlike the infinite square well, there are no boundary conditions to restrict the possible values of k, and hence E. The free particle can carry any positive energy, tacking on the standard time independence, e to the power of negative I e t over h bar. We get this. Now, why did they write it like that? Let's keep reading and we may see. Now, any function of x and t that depends on these variables in the special combination x plus or minus v times t for some constant v represents a wave of unchanging shape traveling in the minus plus x direction at speed v. A fixed point on the waveform, for example, a maxima or a minima, corresponds to a fixed value of the argument and hence to x and t, such that x plus v of t equals constant, or x equals minus v minus or plus v times t plus constant. Okay, I'm a little confused here, but what I remember is, oh, okay, I'm a little goofy with it. They had this here, right? And then they slapped on the time independence or the time dependent wiggle factor, and they just absorbed it into each of these because both of them are exponents, so you can add their arguments respectively. So here we have this one. This is the ikx exponent, and we subtract the wiggle factor, boom. And this is the minus ikx, and we add the wiggle factor because we can factor out the subtraction sign. So same thing, we just apply the wiggle factor to both of these and distribute it. Here, I don't know what's happening, but I do remember if the argument of a imaginary exponential like this looks like x and then minus something t, so x plus or minus something t, that something in front of the t is the velocity. In this case, the velocity is h bar k over 2m. And plus or minus tells you which direction the speed is, the wave is traveling. So if there's a plus in here, the wave is traveling in the minus x direction, so towards the origin or in the minus x direction. And if there's a minus here, like in this case, this is a wave traveling in the positive x direction. Let me take a sip of coffee and just think about this. Kind of weird, but we'll keep reading it. Also, this stuff here, I'm a little confused. I guess they're just saying it's a constant. Okay. Since every point on the waveform moves with the same velocity, its shape doesn't change as it propagates. Thus, the first term in equation 2.94, here, this one, represents a wave traveling to the right, and the second represents a wave, the same energy, going to the left. By the way, since they only differ by the sign in front of k, we might as well write this. So absorb the k into this and remove this b. And we let k run negative to cover the case of the waves traveling to the left. So here we basically completely remove this term, and we notice that there's a minus sign in front of the ik over here. Here there's a plus sign. If we bring the k inside and we let k be positive and negative integers, then that basically takes care of both of these cases with just one equation here, or one term. We let k run negative to cover the case of waves traveling to the left. So k is equal to plus or minus square root 2m e over h bar, with k is greater than 0 for traveling waves to the right, and k is less than 0 for traveling waves to the left. Evidently, the stationary states of the free particle are propagating waves. Their wavelength is lambda is equal to 2 pi over absolute value of k. And according to the de Broglie equation, equation 1.39, they carry momentum p is equal to h bar k. De Broglie, remember this guy. The speed of these waves, the coefficient of t over the coefficient of x is coefficient of t over the coefficient of x. I'm a little confused what that's saying, but okay, speed of the waves, v quantum is the speed of the waves, h bar absolute value of k over 2m, or square root of e over 2m. On the other hand, the classical speed of a free particle with energy E is given by E is equal to 1/2 mv squared, pure kinetics since v is equal to 0. So if we convert this v to momentum and cancel out an m, we get square root of 2e over m. So the classical speed is equal to 2 times the quantum speed. So the quantum speed is half the classical speed. Apparently, the quantum mechanical wave function travels at half the speed of the particle it is supposed to represent. We'll return to this paradox in a moment. There is an even more serious problem we need to confront first. This wave function is not normalizable. So this is an interesting little tidbit they add here, and then they go into normalization problems. Why is it not normalizable? Let's check. Well, the wave function is given over here, right? We determine it is a traveling wave. We try to normalize this, put this psi star psi inside the integral, pull out an a. What's going on here? Why is there no equation in here? But I guess it just equals to infinity, because once you integrate this, if you plug x equals infinity here, this goes to infinity. And if you plug x equals minus infinity, what do you get? A little confused with this one here, but let's see. In the case of the free particle, then, the separable solutions do not represent physically realizable states. A free particle cannot exist in a stationary state, or to put it in another way, there is no such thing as a free particle with a definite energy. So I highlighted this because it just sounds kind of strange. Let's keep reading. But that doesn't mean the separable solutions are of no use to us, for they play a mathematical role that is entirely independent of their physical interpretation. The general solution of the time-dependent Schrödinger equation is still a linear combination of separable solutions, only this time it's an integral over the continuous variable k instead of a sum over the discrete index n. Okay, this is also pretty important actually, so I'm going to highlight this because this is where it gets weird. So here we have the full wave function of the free potential of the Schrödinger equation. So it looks like we have 1 over square root 2 pi integral infinities. Here we have a phi of k, which is a k-dependent function. Then we have the traveling wave here, kx, and then the velocity of the thing times t, and then the integral is dk. But the wave function here is in terms of x and t. So if you integrate with respect to k, this k variable gets removed and everything is left in terms of the variables x and t. So that gives us this thing here. This is a Fourier transform. We're going to see that in a second. The quantity 1 over square root 2 pi is factored out for convenience. What plays the role of the coefficient Cn in equation 2.17? Where's 2.17? Oh, damn, we have to go all the way up. Is the combination of 1/2 square root 2 pi times phi of k dk. Now this wave function can be normalized for appropriate phi of k. So you choose a specific phi of k, and this is a normalizable wave function, which is interesting. What does it mean, appropriate phi of k? But it necessarily carries a range of k's, and hence a range of energies and speeds. We call it a wave packet. I normally don't read these things at the bottom, but let's check it out. Sinusoidal waves extend out to infinity, and they are not normalizable, but superpositions of such waves lead to interference, which allows for localization and normalization. This is crazy. This is absolutely crazy, and this is the first thing that leads us to figuring out why quantum mechanics was actually discovered, because the Young double slit experiment could not explain the interference pattern because it was sending particles through the double slit. Now we have a theory that defines particles in terms of waves, and they can interfere and they can behave kind of like particles if they fly in a wave packet form. So this is where shit gets crazy, guys. In the generic quantum problem, we are given psi of x at t equals 0, and we are asked to find psi of x at t for a free particle. The solution takes the form of equation 2.101. The only question is how to determine phi of k so as to match the initial wave function. Here's what we have here. The initial wave function is written in terms of this phi of k, 1 over square root 2 pi, integral over all of space, phi of k, e to the ikx. So in this case, we remove this thing, right? We just have an e to the ikx, again, integral over k. If you integrate over k, this variable drops off and you are left with a variable of only x, which psi here is left in terms of. So this is like the Fourier transform from psi of x to phi of k. X in this case is position space and k is momentum space. We're going to see this in a second. This is a classic problem in Fourier analysis. The answer is provided by Plancherel's theorem, see problem 2.19. So here we have a general kind of box. Lowercase f of x is equal to 1 over square root 2 pi, integral over all of space, capital F of k times e to the ikx integrated over dk. So you can see here, capital F inside the integral changes to lowercase f once you do the integration. And its variable, the thing that you plug into the f, changes from k inside this integral in terms of dk into this x variable. So this transform is a way of changing between variables. And vice versa. So here we have this line that tells you, if you want to go the other way, if you are given f of k, if you're given the other one and you want to find f of k can be found using this thing. The only difference here is that there is a minus ikx here instead of a positive ikx here. Everything else is the same. F of k is called the Fourier transform of f of x. F of x is the inverse Fourier transform of f of k. The only difference is the sign in the exponent, 41. For some people, some people define the Fourier transform without the factor of 1 over square root 2 pi. Then the inverse transform becomes 1 over 2 pi, integral of this, spoiling the symmetry of the two formulas. Okay, so you don't gotta worry about that, I'll be real. There is, of course, some restriction on the allowable functions. The integrals have to exist. For our purposes, this is guaranteed by the physical requirement that psi of x at t equals 0 itself be normalized. So we're not going to read this 42 because this is some math stuff. We don't care about math right now. We care about the physics. So the solution to the generic quantum problem for the free particle is equation 2.101 with phi of k. Sorry, I wrote earlier when I was reading this book and I can't find a way to erase this. Actually, I can't find a way to erase this. With phi of k is equal to this, and here we put in the initial wave function. Okay, this example is interesting. Should we check it out now? Let's see what else we have left. Okay, and I think that's the end of the chapter. Oh man, that was a weird chapter. You know what, we're going to read the example, guys, because the example is going to be crazy. A free particle which is initially localized in the range minus a to a, so x is between minus a and a, is released at time t equals 0. So the wave function is a between this range, minus a, and 0 otherwise, where a and a are positive real constants. Find psi of x and t. Solution. Okay, so down here I saw that they have a picture. This is what the wave function looks like. It goes here, boom, at point A, it jumps up to a value a, it equals that value, and then boom, it drops down so it equals 0 everywhere else. So this is what the wave function looks like. Now, we're going to plug the wave function into here, I suppose. But first we have to normalize it. So we normalize this, integral over all of space of the absolute value of the wave function squared equals 1. We plug this in, do an integral, do all that stuff. A squared, pull it out, equals 1. 1 over square root 2a is the normalization constant for this wave function. Cool. Next we calculate phi of k. Here is phi of k. Since we have this and it is fully normalized here, and it equals 0 in other bounds, we can change the integral so that it only focuses on the bounds of interest, right? Because here there is a minus a, and here there is an a, there's an a. We don't care about everywhere else because the integral everywhere else will give us 0. All right, so this negative infinity to infinity changes to just the bounds of interest. And here what happens is, well, we have the 2a and an a. Actually, the a is equal to 1 over square root 2a. So that gets pulled out, and this 2 pi gets pulled out from here. Then inside, we don't have anything left because our wave function was just a constant. We just have e to the minus ikx, e to the minus ikx, integration with respect to dx. We integrate that. What is this integral equal to? The integral of this is the thing itself over ikx minus ik, without the x, my bad. Because if you differentiate this, it spits out by the chain rule a minus ik. This minus ik cancels with this one, you get back to the original integral. These two things combine, you can pull out a 2, and then you can combine the pi and an a. And then here the limits are from minus a to a. You plug those in here, and you get this form. So since we plug in a minus a here, this becomes positive, and since we plug in a positive a here into this minus, this stays negative. And we subtract them, so we have a negative here, and we have this I in the bottom, which we keep here. We pull out the k. This way of writing exponentials, this e to the ix minus e to the minus ix over 2i is a way of writing sine. So you can simplify this. You don't have to worry about simplifying this right now, or if you want, you can use Euler's identity, expand this in sines and cosines, expand this in sines and cosines. I think the cosines cancel, and then the I cancels with the I coming from the sine, and you simplify with a sine. Then there's some factors out here in the front. Sine ka over k. Finally, we plug this back into equation 2.101. Let's check 2.101. It is this one here. So what we just determined was 5k. 5k, we did that this way. It was literally just an integral, boom, and we found it here. It was a function, sine of ka over k. We have stuff here. So this is a function of k. Now we plug that back into this, and we integrate again. So here we have the wave packet, the original one, and then our 5k, which we just found, integrate with respect to k, and this gives us the full wave function. Let's see how that looks. This is pretty intense. Integrals within integrals. We plug this into here, boom, pull out constants, boom. Remember that there's a square root 2 pi here, I believe. Yeah, square root 2 pi on the bottom. Integral here and the wave packet. Now how do you do this integral? Check it out. We have dk, right? There's a k inside the exponential, and there's a k here and a k here. This is a crazy integral. Unfortunately, this integral cannot be solved in terms of elementary functions, though it can, of course, be evaluated numerically, figure 2.8, we're going to see down there. There are, in fact, precious few cases in which the integral of psi of xt, equation 2.11, can be carried out explicitly. See problem 2.21 for our particularly beautiful example. I'm going to highlight this, guys. I'm going to highlight this because what Griffiths is saying here is this integral, the free particle integral, is so hard that there are precious few cases when it can be solved by hand and not by a computer. In this problem for a simple wave function, where the wave function was just a constant in this box range here, the integral is unsolvable by hand. So you have to do it with a computer. So he gives you a problem, 2.21, where there's a beautiful example where you can solve it by one. So if you're doing a test and you're not allowed computers, I would study this problem deeply, because maybe, you know, it's complicated and the professor might not give it to you, but it is something that you may be tested on. So I'm just highlighting this because I think I'm going to check this problem out in a bit. In figure 2.9, I have plotted psi of x at t equals 0 and phi of k. Note that for small a, so a small size of the box, psi of x at t equals 0 is narrow in x, while phi of k is broad in k, and vice versa for large a. But k is related to momentum by equation 2.97, so this is a manifestation of the uncertainty principle. The position can be well defined, small a, for the momentum, large, or the momentum, large a. So either you can define the position well, this is a small a, or you can define the possession well, the momentum well, which means the a is large, but not both. So here's the example. Graph of psi, absolute value of psi squared, here, equation 2.105, equation 2.105 here. At t equals 0, the rectangle, and t is equal to this, the curve. Okay, and then a, graph of psi of x at t equals 0, graph of 5k. Okay, so what Griffiths is saying here is here the particle is for sure at this point 0, right? The probability distribution is like centered right there. There's no chance you're going to find the particle here or here. Almost all of the chances you're going to find it here. So since you're for sure the particle is there, its momentum distribution is a little bit wonky. You might find momentum here, you might find momentum here. You'll probably find the momentum here and here. But you could see how the uncertainty principle is kind of shown here. Like here you have localized position and delocalized momentum. And if you flip it around and you have localized momentum, you're going to get delocalized position. So here, I'm not sure, this is showing you, I guess, the same thing. Localized position and delocalized momentum. And it's also showing you what's happening in terms of time. So if I put a particle here exactly, and I wait a little bit, the momentum of the particle is going to like goo it out, and its position is going to become more gooey, and you're not going to know where it is after a while. So this is like the what the free particle does. It also kind of reminds me of the particle in a box. So you can see here, I have this big bump. If I put the particle in the box, and instead of here, there's no walls for the free particle. If I put walls, you can maybe imagine how this like locks into a sine function, like the particle in a box. But in this case, since we don't have walls, it just flutters here and kind of flies away. Anyway, we could just keep going here. I return now to the paradox noted earlier, the fact that separable solution psi of k, of x of and t, travels at the wrong speed for the particle it ostensibly represents. So this is him saying that the quantum speed is half the classical speed of a wave packet. Strictly speaking, the problem evaporated when we discovered that psi of k is not a physically realizable state. Nevertheless, it is of interest to figure out how information about the particle velocity is contained in the wave function. Equation 2.101. 2.101 is here. So how is this represents a free particle, and a free particle moves, right? So how can we pull out the momentum or the speed that this particle is moving at? The essential idea is this. A wave packet is a superposition of sinusoidal functions whose amplitude is modulated by phi. Figure 210. Where is 210? Aha, here we go. A wave packet, the envelope travels at the group velocity, the ripples travel at the phase velocity. Very interesting. It consists of ripples contained within an envelope. What corresponds to the particle velocity is not the speed of the individual ripples, the so-called phase velocity, but rather the speed of the envelope, the group velocity, which, depending on the nature of the waves, can be greater than, less than, or equal to the velocity of the ripples that go to make it up. For waves on a string, the group velocity is the same as the phase velocity. For water waves, it is 1/2 the phase velocity. As you may have noticed when you toss a rock in a pond, if you concentrate on the particular ripple, you can see it build up from the rear, move forward through the group, and fade away at the front, while the group as a whole propagates out at half that speed. Now, what I need to show is that for the wave function of a free particle in quantum mechanics, the group velocity is twice the phase velocity, just right to match the classical particle speed. The problem then is to determine the group velocity of a wave packet with the generic form, boom, the wave function we got from earlier. Except here he replaced the energy there with omega. In our case, omega is equal to h bar k squared over 2m. But what I have to say now applies to any kind of wave packet, regardless of its dispersion relation. The formula for omega as a function of k. Let us assume that phi of k is narrowly peaked about some particular value k. There is nothing legal about a broad spread in k, but such wave packets change speed rapidly. Different components travel at different speeds, so the whole notion of a group with well-defined velocity loses this meaning. Since the integrand is negligible except in the vicinity of k0, we may as well Taylor expand the function omega of k about that point, this point here, and keep only the leading terms. So we expand this in the Taylor series, which is just like the first few. The series continues, but we put this approximation sign here. And this, I think, is omega of k of 0, I think. Where omega prime subscript 0 is the derivative of omega with respect to k at the point k. Changing variables from k to s, which is defined as k minus k naught, to center the integral at k, we have, okay, so we expand this, I see what's going on. So since we're integrating with respect to k, and here we have this, which is a function of k, he expands this in terms of a Taylor series and then plugs this back in here, but changes this variable so that it is s. So now we integrate with respect to ds. So this thing stays the same, 1 over square root 2 pi. Integral stays the same. Phi of k, since we've changed variables, now becomes k naught plus s from this equation. So k is literally just this k here, move it to the other side, s plus k0. S plus k0 gives you k. So we replace that variable inside there. E to the I, kx, in this case kx was replaced by the same thing here, k0 plus s, and the x stays the same here, minus, and then here we have the Taylor series expansion of this thing, and the t stays the same. So the Taylor series expansion is literally omega naught, which is just a number, plus omega naught prime, and then omega naught prime is a function of s there. So a little bit strange what's going on here, but we have an integral with respect to s here, and it seems like you can expand and factor out a bunch of things here and then pull something out of the integral, something which does not depend on s. So here we have an exponent to the I k0x, I k0x. So I'm assuming that is when you factor this x and apply it to this k here. And then minus omega naught, this omega naught here, times t. So we're just keeping this s term here and this s term here. And the rest of the exponentials we can pull out because they don't depend on s. Now we are left with this. And I guess the integral still looks kind of strange, but it still maybe looks like a Fourier transform, maybe. The term in front of the sinusoidal wave, the ripples, traveling speed omega naught over k naught. It is the term in front is a sinusoidal wave. Okay, my bad. This is a sinusoidal wave. The ripples traveling at speed omega naught over k naught. It is modulated by the integral, the envelope, which is a function of x minus omega prime times t, and therefore propagates at the speed omega prime naught. Thus the phase velocity is omega over k, while the group velocity is d omega by dk. Both of them evaluated at k equals k naught. In our case, omega is equal to h bar k squared over 2m, so omega over k is equal to h bar k over 2m, whereas d omega dk is equal to h bar k over m, which is twice as great. This confirms that the group velocity of the wave packet matches the classical velocity. Boom. So this entire thing that he did here was to show this strangeness of the classical speed and the quantum mechanical speed and how they're different. And he says it's because these waves packets that form here, there's the speed of the envelope, which he calls the group speed, and the speed of the ripples inside here, which is called the phase speed. So now he shows this equation here. It's a little bit confusing to me, I'll be real. I got confused in the last few slides, but here we have 1, 2, 3, 4, 5, 6 questions. A very interesting one is this one here. This one has a star on it. We're not going to do it in this video, just talking about it. This one here is also interesting, and I think here we have another problem where you're given this initial wave function and you have to find the final wave function. So that is it for the free particle. Very, very crazy. We're almost done. I think we got 2 more chapters left. In the next video, we're going to talk about the delta function potential. Thank you guys for watching. Peace out.